Hello. As discussed earlier, we are going to start off with the Hooke's law, that is related to the elasticity or the elastic behavior of the given substance, any kind of elastic substance. Now, it states that within the elastic limit, now that is very interesting because we have to consider an elastic limit out of which after which the obviously the object loses its elasticity. So an elastic object need not remain or need not have its elastic property for every moment of time. It will lose it uh, under the influence of an external force which is extreme and which takes it beyond the elastic limit. So this is within the elastic limit. The stress that we apply on an object, on an elastic object obviously, is proportional to the strain that is experienced by it. Now, the stress that we see is usually represented by the force per unit area. It's in fact that's the formula, and the strain that we come across is some change in length per unit length if we are to consider the longitudinal case, for example. Now, if we were to plot a graph for that, we will be observing that we are applying a certain force on any given object, and within that elastic limit, this del L is giving me the extension of that object. So this is more or less what the Hooke's law states. It's a straight line, it's directly proportional. Now you would consider the A and the capital L in the denominator, but they are just fixed quantities. They do not change their value. The area of the surface area on which the force is applied, that does not change. The initial length, the value of the initial length does not change, so they need not be considered in this case. We are just considering the law. By the look of it, we see that the within that elastic limit, the tension that we put on an object is directly proportional to the extension that it is experiencing or that it is undergoing. Now, we have already heard that this phrase that it has to be within the elastic limit. Now, what if it is not within that elastic limit? Then what do we get? So we have this variation of the stress versus the strain curve, where usually we consider the stress in the uh, independent axis and the strain in the dependent, but we will take it the other way around. That doesn't really matter because that is what we have with us at the moment. So this is the stress axis and this is the strain axis. It's easier this way, so the representation has to be in this form. So in this case, what we are observing is that any given object is subjected to an external stress. It follows the Hooke's law and has the elastic behavior. It exhibits the elastic behavior, and that is in that region from O to A, where it is changing directly with respect to the applied stress. Now, what after that? Up till that point A, it was fine. Then that was the elastic limit that has caused it to recover its initial configuration. But now, after applying a further stress on that object, the region AB takes over, And as the strain goes from that point A to the point B, which I am marking right now with some other ink which will be visible to you. So from that point A to that point B that we are observing, that is known as the yield. Now that in that case, what happens is that the there's a we see that point S1 over there. Now if the stress is greater than S1, which was corresponding to the point A, then beyond S1, that is the stress, there is an extraordinary large increase in strain due to that increasing stress, and it does not obey the Hooke's law in that region because that is beyond the elastic limit. Now if the wire is loaded up until the point B, it won't be able to recover its original shape. And as a result of that, there will be a permanent extension in this region. This is the region of permanent extension. Then we continue with the yield, where there will be an irregular behavior. It Even if you consider that there is no elastic limit to that, then you may expect it to break, but all of a sudden you can take the example of a wire that you are stretching, and it's not recovering. It's to the point that it's not recovering its original shape anymore, but it doesn't break as well. And in that case, when you keep on extending it, you see the material or the radius or the diameter of the wire getting thinner, and gradually producing more amount, or extending, or showing off more amount of that substance, and that you take it as the yield of that material. And the point B is therefore known as the yield point. This is the yield point where it starts yielding, and the behavior there is pretty irregular, and in that region from C up until C it's behaving like that. And in that region CDE, what happens is that for a small stress, even for a small stress that you apply, it tends to extend or gets extended by a greater amount, and thereby showing a plastic behavior. So this region CDE is exhibiting the plastic behavior of the material, and from that plastic behavior you end up to the point E, which acts as the breaking point. It is that point where the material can no longer take up the stress, and it finally breaks or divides the body, whatever. And the ratio between the breaking stress, and there's a term called working stress. Now what is the working stress? Now any machine is pretty safe enough if it is subjected to a stress much less than the elastic limit. The stress applied to the machine whereupon it is capable to work under that elastic limit is known as the working stress. Now most of the factories which produce materials, they come up with the factor of safety for a given material. Factor of safety, uh, the factor of safety is given by the ratio of the breaking stress. Breaking stress is the stress corresponding to the breaking point, that is S2 in this given figure, and that divided by the working stress, which is the least stress that can be applied on the material within its elastic limit for its proper functioning. Now this was all about the Hooke's law and the elasticity, but we have also dealt with a term called plasticity. That is the deformation, the complete permanent deformation of the body upon the removal of the deforming force. And we had given the example of wet clay as well. So those bodies are not subjected to these kind of graphical analysis, because they do not possess any elastic properties in the first place, right from the beginning. So the graphical analysis won't lead us to a straight line in case of plastic bodies. Now we move over to the coefficients of elasticity. The coefficients of elasticity are the ratio of the stress and strain. So the coefficient of elasticity. There will be different coefficients because we have dealt with different kind of stress and strain. So similarly, we'll be having different coefficients as well. So in general, it's the ratio of the stress by strain. So that means the slope of the stress strain curve under Hooke's law in that elastic limit is going to give us that. Now this the unit of it will obviously be that of stress, because strain has no unit, so it will be Newton per meter squared and the dimension same as pressure. Now the first coefficient that we come up with is the Young's modulus. Young's modulus of elasticity, usually represented by the letter Y, and that is the normal stress that is applied on an object, extending it longitudinally. So this is divided with the longitudinal strain. Now for any given object, we have supposedly for a wire, which is where the length is the dominant parameter. So we have the force per unit area for the stress that is acting, and this area is obviously the cylindrical area of that area of cross section of that wire, and del L is the extension of that wire divided by L being its initial length. So this is more or less the formula for Young's modulus. It may look like an incomplete expression, but it's more or less like this. So the area can be pi r squared depending on the radius, or pi d squared by 4, that is for the diameter considered. It depends on what you have as the parameter. Now the second one is the bulk modulus, where the bulk modulus is, as the name suggests, for the entire volume, the bulk of the object. So the bulk modulus, the symbols may vary. Somewhere it is beta, somewhere it is in Young's modulus also, somewhere you can be observing the symbol to be gamma, but as for convenience we have taken it Y and B over here. Now this is the normal stress upon the longitudinal, not the longitudinal, but the volume strain. And normal stress is obviously F by A. I'm writing it directly. Volume strain is the change in volume per unit volume. The change in volume goes to the denominator and the initial volume goes up. So that is what we have. Now force per unit area, as you know, is pressure. So that is pressure into volume divided by volume. That is the energy per unit volume, because pressure into area is giving us the energy term. Then finally we have in this case we have another thing that is known as the compressibility, which is the reciprocal of the bulk modulus. So the compressibility of any object is the other way around, because it is not being extended or increasing in volume, it is being compressed the other way around. So compressibility is simply the reciprocal of the bulk modulus, and the unit is obviously similarly inverse of that. Then we have the third term, that is the modulus of rigidity, or the rigidity modulus. which is usually represented by eta, which is the tangential stress upon the shear strain, as you know it, the shear strain that we had studied in the previous case, where I had given the example of the book. It's in the previous video. You can check for yourself. So the tangential stress is usually taken in theta, or is usually force per unit area, and the shear strain is taken as theta or even tan theta, if you remember, but we can restrict ourselves to theta over here. So this is force per unit area multiplied with the theta, which is the strain, that is the tangential strain in this case. So this is the coefficient of elasticity in various forms that we just studied. Now the temperature does have an effect. All three coefficients that we have just studied, they depend on the temperature. For very small changes in temperature, all of them obey the linear law of change, and the variation is somewhat like this. That is, let's take for the example of the Young's modulus that we have. Young's modulus at a given temperature is equal to the Young's modulus at say an initial temperature. Let me take it as Ti. This is Tf, this is the final temperature, and then that minus alpha, which is the coefficient of temperature coefficient in this case, minus the final minus the initial temperature, or the temperature difference. Similarly, we have that for the rigidity modulus and the bulk modulus as well. It's the same expression. You can take the coefficient of temperature, that is the temperature coefficient, as beta and gamma respectively for them. Up next, we are calculating, or we are obtaining the expression for the work done during expression, which eventually leads us to the energy density of the given object. We'll see how. Now for an extension in the longitudinal frame, or in the lengthwise extension, we have the Young's modulus, where FL divided by A, and supposedly the object was extended through a distance x. So we know that force will obviously be equal to the Young's modulus multiplied with the area divided by the initial length into the extension. Now if dW is the small amount of work done in order to extend the given object through a distance dx, then that is lengthwise, of course, then we have the work done to be equal to F times of dx, and that will be equal to, as far as the expression of the work goes, this multiplied with dx. So the total work done can therefore be obtained by integrating dW over the whole range of work YA divided by L if the extension is taken from 0 to a final distance, let us say small l. Then we have the x dx over here. We have the x dx over there. So that is going to give us YA divided by L, x squared by 2 taken from 0 to L. So that is YA by L, and this is L square by 2. The 2 can come up over here. Now it's pretty simple, but what we are going to see is a new form of it, that is YA by L multiplied with that extension. The 1 by 2 factor goes to the left, and we multiply the other L alone, leave it like that. So This, as you can see, is the expression for the force. If you observe this, this is the expression for the force. The expression is YA divided by L into the extension, which is exactly the case over here with the extension being small l. So this is half of F times of L, which is again the extension. So that is half times of the tension times of the extension. Now force into length is going to give me the work, and the energy density that we had considered is nothing but the energy per unit volume, and this energy is nothing but the work done. The work done is stored in it in the form of potential energy, as we know. So work done per unit volume, that is half of F times of L divided by A into L, which is the total volume of that substance. So L's get cancelled out. What we are left with is half of F by A. But we also no no the total volume is the capital L. So with the we are not done away with the um, L's. They remain as such. Interestingly, what we are getting is half F by A is stress, and the other one is strain, and that's the expression for energy density. Very important formula as related to the topic on stress and strain and modulus of elasticity, uh, mostly related to the numericals. From the numerical point of view, it's quite an interesting and important relation. Now, what's even interesting is the fact that if you consider two materials such as steel and rubber, you end up getting steel, sorry, that's wrong in terms of the spelling part. You end up getting steel is more elastic than rubber. Pretty interesting. Who would have thought that rubber is going to be less elastic than that rigid fellow steel? That's because the extension of steel is less than the extension of rubber for a given stress. It's as simple as that. You apply the same amount of stress on a steel bar or a steel pipe, and the same amount of stress on a rubber. Obviously, the rubber gets extended, and the more the extension, the more is the value of the strain. And with greater strain being there in the denominator for a given modulus of elasticity, we have a lesser coefficient of what do you call it? The coefficient of elasticity. So the coefficient of elasticity is of that of steel is obviously going to be greater than the coefficient of elasticity of rubber. That is, let's say the Young's modulus of steel is greater than the Young's modulus of rubber. Why is that? As I told you, that the extension of the steel will be less than the extension of the rubber for the same stress, for the same F by A, force per unit area. You take the same area of the steel as well as that of the rubber, you take them cylindrically to be having the same area of cross section and of same length. For the same amount of force, the rubber will be extended by a greater distance, and as a result of that, the strain factor in that will be greater, and as a result of that, the modulus of elasticity, that is the Young's modulus in this case, will be greater for steel than that of the rubber, and hence we get such a result. Now we can have one more ratio to work with. We call it the Poisson's ratio. I'm squeezing in that point over here. Uh, so what do you mean by the term Poisson's ratio? Now if we are extending something, some object lengthwise, we are reducing its diameter for sure. I'm drawing the figure over here. So this is an object. We are applying a certain force to it and dragging it down supposedly, and it's going down, it's elongating. It's obviously fixed initially to a rigid support, and as a result of that, it's extending, but at the same time it's reducing in its diameter. So this extension, the volume remaining same, obviously causes this to happen. The length increases, there has to be a decrease in the volume. So we define the lateral strain and the longitudinal strain in this case, and from that we take the ratio of the lateral strain to the longitudinal strain. So Poisson's ratio, usually it is represented by the symbol sigma. You may come across some different symbols, but usually it's sigma. Sigma is equal to the lateral strain divided by the longitudinal strain that's the Poisson's ratio for a given material of a given wire maybe, and it's obviously it's a unitless quantity. Limiting value of the sigma, that is the Poisson's ratio, that lies between -1 to 0.5. Now these, having studied about the coefficients, that is Young's modulus, bulk modulus, the rigidity modulus, you may be interested in obtaining the relation between them. So I'm giving you a few relations, and it's on you to try out these relations in case you wish to find them and obtain the results. So I'm taking a fresh page for you for the relations. The relations are as follows. Suppose we have the first relation as the bulk modulus to be equal to the Young's modulus divided by 3 1 minus 2 sigma. Sigma is the Poisson's ratio that we just studied. Then we have the second case. We have the rigidity modulus to be equal to the Young's modulus divided by 2 times of 1 plus sigma. The third relation, 9 divided by y is equal to 3 divided by eta. Eta, once again, the rigidity modulus that we have with us, plus 1 by the bulk modulus, reciprocal of the bulk modulus, which is obviously the compressibility. And finally, another relation where we have the Poisson's ratio to be equal to 3 times of b minus 2 times of eta divided by 6b minus, not minus but plus 2 eta. So these are few relations which you may try. My proposal that you just apply those formulas and you will compare the left hand to the right hand, and you'll get it pretty easily. It was easier when I had obtained it, so I hope that it's easier for you as well. You can always try. In case you find it difficult, you can let me know and I'll provide you with a video on it. Till then, so that was all actually from this topic on elasticity. It has various uses, of course, the bridges and the ropes that are built, many uses. You can check the internet by yourself, where you can come across various uses. In fact, you can let me know about those uses in the comments. Till then, thank you for watching. We'll start off with a new topic in the next video.